Okay, hello everyone. Let's go ahead and take a look at the modulus of z. Now remember that what we said is that we have any particular z, any particular complex number z, written as a plus bi. And we know that that can always be diagrammed using a two-dimensional vector. As we see here, z is equal to 3 plus 2i. We have the particular complex number drawn in the arc diagram. Now, being that it's a vector, all vectors have direction and magnitude. And so what we're going to focus on today is the magnitude. Now, if we go ahead and interpret the vector's magnitude, then of course we can go ahead and use the same techniques using the Pythagorean theorem to determine exactly what the length of this particular vector is. And we know that it's going to be equal to the square root of 13 in this case. Well, we're going to talk about it using a slightly different term. Instead of calling it the magnitude of z, we're going to call it the modulus of z. And again, being that it's going to be a length, then it is always going to be greater than or equal to 0, and it's going to have exactly the same representation as if the vector was in two-dimensional, the real coordinate plane. So one thing that we also want to go ahead and take a look at, though, is that if we go ahead and take a look at z times it by its own conjugate, notice that we come out with a squared plus b squared, which is exactly the same thing that we're coming out under the radical for the modulus. So one interpretation of the modulus then could also be the square root of the complex number multiplied to its own conjugate. Now there's going to be 6 properties that we're going to investigate and prove as well, and these are there. One says that we take the modulus of z, and it's going to be equal to the modulus of z conjugate. This number 2 we've already just went ahead and discovered by squaring both sides. We also are going to be able to find out that the modulus of the product of z sub 1, z sub 2 is going to be equal to the product of the moduli. And also the same thing with regards to the division. We also are going to be able to see that if we go ahead and take n number of complex numbers and multiply them together and take the modulus of the result, it's going to be exactly the same thing as the individual moduli multiplied together. And the last one here is saying that if we go ahead and take any particular complex number, raise it to a power, and then take that and then find the modulus of that, it is exactly the same thing as taking the modulus of the original complex number and raising it to the exact same power of n, so long as n is an element of the real integers. So, just to wrap things up again, we know that we have a two-dimensional vector representation for any complex number, and being that it is a vector, it has direction and magnitude. In order to go ahead and calculate the magnitude, or what we will more appropriately call the modulus of the complex number, we do exactly the same thing as we would when we found the magnitude of a particular vector in the real number plane. So we have the 6 properties which will also come up as a result of us dealing with complex numbers. Okay, so there you go. We'll take a look again at these 6 properties and also hopefully be able to prove every single one of those. See you later. Bye-bye.